All right. Well, what we talked about last time, we went through, we talked about what conduction are, the modes of heat transfer, where Fourier's law comes from, right? And then we went into 1D steady state conduction and did a little bit of an analysis on this problem, right? This problem where we have some cylindrical tube and we're trying to model the temperature profile across that tube. So we went through the process of deriving an ordinary differential equation, right? This what we call a governing ODE. It's governing the behavior of the problem. And we express it in terms of temperature, and you see that at the top. That was kind of our final result for this problem. It's a relatively simple expression. Okay, and we left, before we finished, we left with not having yet addressed the boundary conditions. Okay, so when we, kind of where we left things off, we said we had a temperature expression. We said T is a function of R, right? And this temperature expression was, what we solved was some unknown constant of integration times the natural log as a function of R plus another unknown constant of integration. Okay, so this expression, while it is accurate for what we're talking about for this problem, it doesn't actually fit the specific problem that we have, right? Nothing in the C1 and C2 indicate how this relationship maps to this problem. Okay, so in order to get that equation to map to our problem, we have to enforce boundary conditions. All right, boundary conditions are, physically what we're looking at is what is the domain that we're trying to model. We're trying to model in the R direction, so we need boundary conditions in R. We need to look at the edges of the domain in the direction we're modeling. Okay, so this would be for this problem, R in and R out. That's where we're going to look for our boundaries, or boundary conditions. And then in this problem, it's really simple, right? We have TH at R in, and we have TC at R out, and we just need to find a way to enforce that onto our equation. Okay, so to state this mathematically, right, this is our governing ODE here. This is boundary condition number 1. Let me just write it, boundary condition number 1. And this is boundary condition number 2, right? TR equals RN equals TH. And so like, how do we actually force that equation up there to satisfy these boundary conditions? Well, all you do is you say, okay, my expression for temperature here is given by this equation up here. This equation up here. So for 1, I would just write out my expression evaluated at R equals Rn. So I'd say C1 times ln at Rn. Right? We're evaluating at R equals Rn plus C2 is equal to TH, right? The temperature at that position. All right, the second boundary condition is basically the same thing. We have 2 temperature boundary conditions, so C1 ln R out plus C2 is equal to TC. Okay, so now we have a set of equations, right? 2 equations and 2 unknowns, or 2 unknown constants, and we can solve these. In this case, it's really simple, or we could solve it explicitly for C1 and C2 and have analytical expressions that we can then plug in to right up here, right? These constants. Right, and then we have our full solution for this problem. Okay, so what we want to do today is I want to introduce Maple to you guys. We can go through how to use that tool. That's something you're probably going to want to use in short order here, probably on the first homework to some degree. So we'll go through how to use Maple. And I think the easiest way to do it is let's just take this existing problem, which is pretty much a trivial problem. Like, this is really easy to do, but we'll use Maple to solve it, so you can kind of compare directly what's going on. Okay, so this is kind of the steps we'll follow. Again, Maple is I have it open on a computer here. Hopefully you can see as I write. Okay, so Maple, as I said last time, is a symbolic mathematical tool. It's a symbolic solver, meaning it will take expressions that you give it, and it'll solve those expressions in whatever situation you want. Right? As opposed to something like MATLAB or EASE, where it's actually looking at the numerical values that are represented by the symbols. Here we're looking at the symbols themselves. So this makes it really powerful and really useful for a lot of the analytical modeling that we're doing. Okay, so you get Maple either through XenApp or install it on your computer. You launch it, it looks something like this. Okay, there's kind of different ways of starting this program. So you can do a new document. You can either do a new document in worksheet mode or document mode. Document mode is the default for whatever reason. Worksheet mode is actually the one that I think is more directly useful. Document mode, you can like annotate and write, like formatted text alongside your equations. So it's kind of like markup, but I think we usually just use it for math. So in worksheet mode, if you launch it, it should look something like this. If it doesn't, you can play around with these drop downs to get what you want. But here's your prompt. Okay, so the prompt is where we'll just start typing. And so the first thing we want to do is we want to clear out anything that's existing in memory, right? If you're just running multiple worksheets, we would hit restart. So restart is our first command. You want to know anything about these commands, you would hit, I guess, hover over it or something and hit, I think, F2. Okay, so an F2 will take you to the command page for that. I'm sure there's like a help menu option there too. So restart. Okay, and you can see I put a trailing semicolon here. If you put a trailing semicolon, that will show any output coming from the program. If you put a trailing colon, then it will suppress any output. So you still execute the commands, but it suppresses any output. So we'll just do semicolon, we restarted. Okay, so what we want to do is, let's see, what's our goal here? So let's look back. So we want to solve this equation that we came up with, this governing ODE for temperature, and then come up with a solution specific to our problem, basically solve it the same way. So let's start with this DDR, RDTDR, this ODE, and let's figure out how to enter that in. Okay, so the first thing you want to do is use what's called the diff command. Diff. And so diff is taking the differential of any function that you have. So let's say, I wanted to take the differential of x squared. All right, so I'd enter in that expression, comma, and then the variable that I'm taking the differential with respect to. Okay, and then if you hit enter, there's our derivative. Sorry, it's small. Actually, I don't know if I can make this maybe a little bigger. Let's try this. Right, so x is the derivative of x squared. In this case, we actually want the derivative of a temperature, right? Temperature with respect to radial position r. Okay, so if I did this, it's going to give me back 0, right? Because I haven't told it anything about what t is. It thinks by default anything you put in there is a constant, unless you tell it otherwise. So we actually need to put in here t is a function of r. We do that by parentheses r, and then we execute that, and you're going to see, all right, now we have a differential operator on our function t of r. Okay, so let's actually enter in the equation. We had DDR RDTDR equals 0. Okay, so we have diff of r times t of r. So we're nesting these together with respect to r is equal to 0. Right, and there's our expression. So we're at this point just telling Maple, this is the expression that we're going to end up solving. We haven't really done anything yet. We're just kind of telling it what it is. Okay, so then let's go back. So next step, we've used our diff expression here. Next step is we're going to solve this. We're going to solve this for t as a function of r. That's done with the dsolve command. So dsolve. Let's see. So, all right, so dsolve, we're going to solve this thing up here. But now instead of entering this in manually, it's really handy to name things or like keep track of names on these. Okay, so let's call this ODE. Okay, and if we call it ODE, we can assign it using this operator colon equals. All right, so colon equals assigns that thing, that expression to this name, right? ODE. Okay, so ODE is now that. So we're going to dsolve ODE. All right, so dsolve ODE returns our solution, just like that. So rather than going through that full integration, the multi-part integration that we did, which honestly wasn't that hard, but it was some work. This just straight out tells us, here's your answer, right? And then notice that it has the unknown constants of integration in there as well. Okay. All right, so next up, we've got our general solution. So now we want to actually evaluate this expression at the boundary conditions, right? So let's actually call this something so we can use it again. Call this, come on, I can get it to go over there. We'll call it TS. That's our solution. Okay, so the first boundary condition, I wish it would just stay at 18 or whatever. Okay, so the first boundary condition, we'll call this BC1. And so we're going to evaluate this expression using the function eval. Okay, so eval works like this. We say eval. We're going to evaluate the expression TS, the thing we called TS. We're going to evaluate that at some value of R. So we'd say at R equals Rn. Okay, so we do that. We're evaluating R equals Rn. And then we're going to set that equal to TH, right? That was I believe, our first boundary condition. Okay, so we do that, evaluate it, and you can see, all right, sure enough, we have T evaluated R equals Rn equals the constants evaluated equals TH. Now this is a little bit messy. We don't actually want that TR equals Rn, like it's kind of duplicating itself. So if we just want part of the solution, TS, right? For TS, we don't actually want this part of it. We just want this part of it. So we would limit the solution to the right-hand side. So RHS is the function here. Okay. So now we have our RHS. Yeah, next time I'll figure out how to get it to stay at the right font without having to do this all the time. Okay, BC2 is the same thing. We're going to evaluate that. RHS of TS at R equals R out, and that is equal to TC. All right, so there's our two boundary condition solutions. Okay, then how do we get all this stuff back together, right? This is kind of so far just busy work, basically. It's not really helping us that much. But I mean, maybe you can imagine for the more complicated problems we're going to be doing, or there's more derivations involved, this could be really useful. But really where I think Maple's super useful, besides having the derivatives and integrals all built in, is solving for simultaneous sets of equations. Okay, so here what we're going to do is we're going to solve for the unknown constants. So we're going to say solve. We want to solve for C1 and C2, and we have to tell it which equations are going into that solution. Okay, so we're going to solve for, this is curly braces. God, that's so hard to see. So we'll do curly braces. What are we solving? Let's see. So the syntax is the expressions we're trying to solve, so BC1 and BC2. And then what are we solving for? We're solving for C1 and C2. Right, you could use this equivalently without solving for multiple at once. Like if you just wanted to solve for BC1 in terms of C1, you could just use solve for that. But this way we're solving both together. So you do that and you end up with a solution in terms of C1 and C2 explicitly, right? Very explicitly solved for there. Okay, we'll call that, let's go back and call that something. Let's call that constants, that. Okay, and then now we can actually go back and substitute this in. And this is kind of the last step. So we're going to sub in, let's say TS is now equal, we'll reassign TS is equal to subs of our constants. Oh, that's really bad spelling of constants. And we're going to substitute that into our original expression of TS. Okay. Again, let's make this so you can see it. And now we have an expression, T as a function of R. So now t is a function of r. You can see r appears in the expression. But this is our specific solution for this problem with the boundary conditions enforced. Okay. Any questions on this so far? It's all pretty straightforward. Okay. It becomes less straightforward, I think, when you sit down and try to do it. But if you just follow these steps as they're kind of outlined here, hopefully that'll get you most of the way. There are some maybe useful things that you can do. One function is called simplify. So simplify, if I wanted to simplify this expression, I could do that, right? Oh, by the way, another way of, instead of naming everything, if you just want to go in a sequence, you can use this percent sign. Okay, so if you say simplify percent or something percent, percent is just the last thing that was evaluated. Okay. You could also do this. So if you simplify and then double click on the number, it'll simplify the equation that's numbered linked there. Okay, so if we do that, okay, it changed it slightly. It's not really that much of a simplification, but it helped a little bit. Okay, so now we have our solution, right? You can take this, you could just copy it and paste it right into ease if you wanted to solve it there or evaluate it there. But this is generally a pretty useful workflow.